So now let's continue that chemical bonding with a new concept, with a new type of bonding, that is hydrogen bonding. So we have already seen three categories of bonding. One with the force is less than 8 kilojoule, one is force between 8 to 42 kilojoule, and one the force of interaction is greater than 42 kilojoule. So that lies in the middle category, where bond energy is equals to from 8 to 42 kilojoule per mole. So here the bond energy lies between 8 to 42 kilojoule per mole. So it is shown by that molecule in which hydrogen atom is directly attached with more electronegative atom like fluorine, oxygen, nitrogen, where electronegativity is greater than equals to 3. So in the bond that is shown by the molecule in which hydrogen atom is directly attached with a more electronegative element like these, and sometime with chlorine, and sometime with chlorine, and with sp hybrid carbon atom with chlorine. Okay, chlorine always exhibit chelation. Okay, here it will always exhibit chelation. Okay, chelation means the tendency to form a long chain, and with chlorine will also with sp hybridized carbon atom, with sp hybridized carbon atom. So with sp hybridized carbon atom, example like HF, hydrogen fluoride, there are n molecule. Okay, H2O, hydrogen directly attached with more electronegative like fluorine, oxygen, and nitrogen, and in NH3N. So they are actually liquid at room temperature. HF and H2O, they are liquid at room temperature. Okay, this is the denotation that they have a very strong hydrogen bonding. And ammonia, it has weak hydrogen bonding. It is a weak hydrogen bond. So that is gas at room temperature. Okay, it is gas at room temperature. If we talk about like HCN and HCN, okay, if we consider one more example, HCN and HCN. So here, if we see nitrogen has delta 3 negative charge, and it is delta negative minus this is sp also. Okay, and it is delta positive. Again here it is delta positive. If we break this bond, the electron will go which side, which is more electronegative. So it is delta negative and 3 delta positive. Okay, again here delta negative, and here also 3 delta positive, and nitrogen has 3 delta negative charge. Okay, how we decide which is delta positive and delta negative? If you break this bond, where the electron will go to the more electronegative element. So nitrogen is more electronegative element. So if you break this will have 3 delta positive, and this will have 3 delta negative. So we know that nitrogen. Okay, so then there is also hydrogen bonding. Okay, it is also hydrogen bonding, because it is very, now hydrogen is forming a nitrogen. Okay, this is also hydrogen bond. Okay, so that we will also consider hydrogen bond. So we see the order of order of molecular force of attraction. So what is the order of molecular force of attraction? What is order of molecular force of attraction? So we see when type of forces are different. First case, when we are considering the type of forces, type of force of attraction are different. Type of force of attraction are different. So we know we have listed a lot of type of force of attraction in the previous video. So now we know when type of force of attraction are different, then which will be having the most strong molecular force. First is hydrogen bond. Hydrogen bond means It is stable dipole interaction. That is stable dipole attraction means the dipole which are stable. Here if you see HCl HF, they were stable dipole. They were not affected by the outer solvent and outer conditions. Then next is Keson. That is weak dipole attraction. That is a weak dipole attraction. Dipole attraction, weak dipole attraction. So like hydrogen bond, what is the example of hydrogen bond? Like hydrogen fluoride. So this is the example of hydrogen bond which is a stable dipole attraction. Okay, so this is the example of hydrogen bond. Then next is Keson. Okay, weak dipole attraction. Next is Debye force. DEBYA, that is Debye force. Debye force means it is a dipole induced dipole. That is dipole induced dipole. Next is London forces. London forces means that is induced or induced instantaneous dipole. That is induced instantaneous dipole. So type of attraction. Okay, so there are four. Okay, therefore the strongest is hydrogen bond, then Keson, then Debye force, and that is London force. So these are the four category of type of molecular force of attraction. So if we talk about what is Keson, Keson force are when X equals to chlorine, bromine and iodine, and the bond are HX. So that is known as Keson. Okay, this bond is known as, this force, molecular force of attraction is known as Keson, and that is weak dipole attraction. That is weak dipole attraction. Weak dipole attraction. So that is Keson force. Next, if we talk about next is Debye. Okay, next is Debye. So Debye, it is HBr. Debye, what was the? It is dipole induced dipole. So we know that HBr is a dipole. Okay, it is dipole. Now if we have again one molecule where the dipole moment is 0, but as it comes in contact with bromine, so there is little delta positive charge generated and then little delta negative charge generated. Okay, so it is induced dipole. Actually it is induced dipole. Okay, from what is induced? It induced with HBr. HBr induced the dipole. Okay, so initially it is not dipole, but it is induced by HBr. So it is known as induced dipole. Okay, this is dipole, this is induced dipole, and that weak, then this force is known as Debye. DEBY. That is known as Debye force. Debye force. If we talk about again like one more example, like CL3 having bond with bromine and bromine, so it is polar. We know it is polar, but it is again non-polar. So this is again the dipole induced dipole. So this is also again Debye force. Debye force. Now let's talk about London forces. Okay, London forces. So London forces was induced in instantaneous dipole. So like we have X, any dipole. Okay, any non-polar molecule. So the force of attraction between them, it is known as London forces, which is the weakest force among all these type of forces. Okay, so that is our London force. Okay, so now these were the categorization of which force should be there, which force should not be there. Okay, now let's talk about all the properties like melting point, boiling point, and critical temperature. Okay, melting point, boiling point, critical temperature. Okay, they are directly proportional to molecular force of attraction. That is molecular forces of attraction. Okay, now they are directly proportional to molecular forces of attraction like hydrogen bond and van der Waal forces. Okay, hydrogen bond and van der Waal forces. So we know hydrogen bond and van der Waal forces, they are directly proportional to van der Waal forces. Now we know that molecular force of attraction. Now how it is so? We know melting point of boiling point. When the force of attraction between them is high, so we need more energy to boil them. We need more energy to evaporate them. So and critical temperature also should be more. Melting point is also depends on type of interaction of the force. So melting point, boiling point, and critical temperature, they all depend on the type of interaction between the molecules. So that's why molecular force of attraction, they depend. Okay. So now if we talk about the second case, when type of molecular forces are same. Okay, if we are talking about the second case, when type of molecular forces, when type of molecular forces are same, so then when type of molecular forces are the same, then magnitude of the van der Waal force of attraction, magnitude of van der Waal force of attraction is directly proportional to molecular mass or atomic mass of species. Directly proportional to molecular mass or atomic mass, molecular mass or atomic mass of species. Okay, now when molecular forces are same, we have categorized all four molecular forces. Now when molecular forces are same and same, and how we differentiate which should have more molecular force and which should have less molecular force. So type of molecular force are same, then magnitude of van der Waal force of attraction is directly proportional to molecular mass or atomic mass of the species. Now again, if we categorize them, when molecular masses are equal, okay, if we talk about when molecular masses are equal, then in case of isomer, when molecular masses are equal, in case of isomer, then magnitude of van der Waal force, then magnitude of van der Waal forces, then magnitude of van der Waal forces is directly proportional to surface area of species. Directly proportional to surface area of species. Okay, now we know that then when now first type of force, then after type of force are same, then we call them molecular mass. When molecular mass are same, then surface area depends on the surface area. So now let's understand this by an illustration, like the illustration, compound with maximum boiling point is, okay, now we have compound with maximum boiling point, compound with maximum boiling point. We have four options. A is hexane, that is C6H14. B is neohexane, that is C is isohexane, and D is can't be predicted. Okay, now if we talk about all the forces, we know boiling point, melting point, and critical point depends on molecular force type of interaction. Now are all the forces are same? We know all are all forces are same, and molecular masses are same. Actually, they are isomer. Okay, so we will talk about their surface area. So if we talk about A option is simple hexane. B option is neohexane. It is 1, 2, 3, 4, 5, 6. Okay, and C option is it is neohexane. Okay, so neohexane, so it is 1, 2, 3, 4, and neo compound 5 and 6. And isohexane is 1, 2, 3, 4, 5, and this is an iso. Okay, so now it has the more surface area, and the surface area is more surface area. Here it has least surface area, and here it is has a less surface area, area. So if we talk about so answer is hexane. Hexane is maximum. Hexane has maximum boiling point. Then isohexane, by isohexane. Then it is a neohexane. Then neohexane has the least surface area. So now that will be the order of their boiling point. As branch increases on carbon, the molecule acquire more and more spherical shape. So surface area decreases. Okay, so it when it is more branched. Okay, why more branched? As more branched means more spherical area. Okay, means more branch means more spherical shape. More spherical shape means less surface area. So less surface area, that's why the neohexane is the least among them. Now if we talk about the order of force of attraction, okay, now if we talk about order of force of attraction, that is helium, then neon, then argon, then krypton, then xenon. Okay, so this is the force of attraction between them. Okay, here we again directly proportional to the molecular mass. If type of forces are same, then it is directly proportional to the molecular weight. Okay, now if we talk about further in H2S, H2SE, H2TE, H2TE, that is H2TE, then H2O. This is liquid at room temperature. This is liquid at room temperature, but this is hydrogen bond. Okay, we all know this is gas and this is liquid. Now actually it should be there because less molecular mass, but first we will consider type of force. So here type of force we will be seeing gas at room temperature. Okay, type of force we see here, it is a hydrogen bond. Okay, that's why it comes forward. Then type of forces are same among them, that's we are considering the molecular mass. Next, CH4 is greater than SiH4 is greater than NgEH4, then SnH4. Okay, they according to their molecular weight. Okay, now again if you see F2, Cl2, Br2, then I2, then also that will be according to their molecular weight because type of forces are same. Okay, now let's consider a question. So first of all, you know all the information, so you may pause the video and answer by your own. Okay, now you may pause the video and compare each and every molecule and answer by your own. So now let's talk about again. If we compare Cl2 and HCl, we know that here we have London forces and here we have Caisson force. So we know Caisson force is greater than London force. Here we have same type of force of attraction. Then we will talk about according to their mass. Okay, here and there are whatever force. There are London force. Okay, now if we talk about HBr and HF, we know it dominates because here it is hydrogen bond is there. Again this dominates because here it is hydrogen bond. Xenon and argon, we know that are same force, that depends according to their mass. Between these two we know this is a urea which is a solid, and here it is a hydrogen bond. Okay, this is acetone, that is liquid. Acetone which is a liquid. So we know that solid has obviously more force than a liquid. If we compare that with alcohol and ether, so we know alcohol it has a hydrogen bond and ether don't have, so hydrogen bond. Okay, now if we compare C4, HA, and they all have the same force, then we will answer by their mass. If we talk about D2 and H2O, it is normal water. So now let's talk about H2O and D2O. Where H2O is considered as normal water, it is considered as a normal water, and D2 is considered as a heavy water. Okay, heavy water. So we know normal water, heavy water. Answer according to their molar mass. So heavy water is our answer. Now let's one more important question which was previously asked in J, that C sigma 1 C bond energy is 100 kilocalorie per mole, 10 kilocalorie per mole, and it is 1000 and 100 kilocalorie per mole. So answer is 100 kilocalorie per mole. We know that that answer is 100 kilocalorie per mole, which is we have already seen that when there is a greater than 82 joule per mole, okay, kilojoule per mole. So that should be greater than, okay, 10. So greater than 10, answer is 100. Okay. So now if we look at further. So now we are talking about some exceptions cases. So hydrogen is greater than helium, the boiling point and melting point. Here surface area dominates over the mass. Okay, now second, ammonia is less than that 10 SbS3, and ammonia is greater than, boiling point is less and melting point is more. So melting point more justify the hydrogen bonding, but here the mass dominates over hydrogen bonding. Again here also mass dominates over hydrogen bonding. Okay, so that's why HI is greater than the melting point. Okay, here it is melting point is greater, here boiling point is greater. Again here the force of attraction could be the induced dipole induced. Okay, so now that but here it is now London force of attraction. Okay, so that dominates, mass dominates over them. Okay, that's a boiling point order is that. Again here the boiling point that NHMe2 is greater than NMe2, here boiling point. Okay, here the mass doesn't depend. Okay, here that's why boiling point is this. Again here HNMe3 and greater than NH2Me, here boiling point is greater. Okay, so that's why the hydrogen bonding loses here. Here it is boiling point, and here again it is boiling point. So that's are the some exceptional cases. So now let's talk about boiling point, melting point, and critical temperature of covalent compound, that directly proportional to magnitude of van der Waal force of attraction or hydrogen bonding. That is van der Waal force of attraction, or we can say that is hydrogen bonding. So that depends on the magnitude. Okay, when in case of covalent compound, now boiling point, melting point, and critical and of ionic compound, if we talk about ionic compound, that directly proportional to lattice energy, and lattice energy, the formula is given by QA plus and QC minus, that is radius of cation plus radius of anion. Okay, so radius of anion. Okay, so here it should be radius of anion and radius of cation. So that radius of the charge on anion, charge on cation divided by radius of cation and radius of anion. So we know chemical bond can be formed by two ways. Okay, whenever we talk about a chemical bond, that can be formed by two ways. Okay, one is by complete transfer of electron. Okay, by complete transfer of electron, and next is by sharing of electron. Okay, so here we get the bond covalent bond, and by sharing of electron we again get metallic bond, and in by complete transfer of electron we get ionic bond, one we get ionic bond, and one we get electrovalent bond. So these two types of bond we get by chemical bond, by chemical.